Hi, we're going over the review for 6.1 to 6.3. Number 1. According to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. Label the normal distribution below. So the mean goes in the center, 149, and then we count up by our standard deviation from there. So we're counting up by 9. So we have 158, then 167, and then 176. Labeling back, we also subtract the standard deviation. So from 149, I subtract 9, I'm at 140, then 131, and then 122. We can drop down our lines at each of these points, the mean and 1, 2, and 3 standard deviations away. And then we can use our empirical rule to label the percents. So between the mean and 1 standard deviation away, that's 34%. From 1 standard deviation to 2 standard deviations away, that's 13.5%. From 2 to 3 standard deviations away is 2.35%. And all of these are listed on your formula sheet. And then the remaining outside of 3 standard deviations away is going to be 0.15%. Okay, what is the probability a randomly selected 12-year-old boy will be over 158 centimeters tall? So this one I'll highlight over 158 centimeters tall. We're looking from here, 158 and above. So we can take these quantities and add them together. 13.5 plus 2.35 plus 0.15, and that's going to equal 16%. For the next one, what's the probability a randomly selected 12-year-old boy will be between 131 and 140 centimeters? So between 131 and 140 centimeters, that's going to be from here to here. So that's just 13.5%. What's the probability a randomly selected 12-year-old boy will be between 149 and 167 centimeters tall? So 149 to 167 is going to be from here to here. So we can add 34 plus 13.5, which is going to give us 47.5%. What's the probability a randomly selected 12-year-old boy will be at most 131 centimeters tall? So at most 131, that means 131 and below. So we can add together 0.15 plus 2.35, which gives us 2.5%. Now, the other way you can do these, if you do not like using the empirical rule, is you can use normal CDF and use the mean and standard deviation. So I will write those as an alternative way to do them. So for B, you could do normal CDF, 158 up to 10,000, and then 149,9, and that gives you 0.1587. For C, you could do normal CDF, and then we would have 131 to 140, 149.9, and this would give you 0.1359. For D, you could do normal CDF, 149 to 167, 149.9, and that would give you 0.4772. And for E, you could do normal CDF with negative 10,000, 131, 149.9, and get 0.0228. So the empirical rule percents you can see are nicer, rounder numbers. Again, we're using that empirical rule. Normal CDF, you're getting a more exact using the normal distribution, but either of these solutions would be fine on the quiz. Letter F. Henry is 161 centimeters tall. How many standard deviations above the mean is his height? In other words, what is his z-score? So we use the z-score formula. Z equals x minus mu over sigma. So z equals 161 minus 149 divided by 9. And this comes out to 1.33. So in other words, z is 1.33. Kevin's height is 0.65 standard deviations below the mean. In other words, his z-score, z equals negative 0.65. What is his height? Again, we can plug this into the z-score formula. So z is x minus mu over sigma. Negative 0.65 equals x minus 149 over 9. And so you see we can multiply by 9 and then add the 149. So x is negative 0.65 times 9 plus 149, which will give us 143.15. So he's 143.15 centimeters tall. All right, for our next section, we're finding the indicated probabilities and shading the corresponding area under the standard normal curve. So for A, probability z is less than or equal to 0.75. So remember, standard normal distribution is centered at 0. We count out, here's 1. So z is less than or equal to 0.75 is right here. Z is 0.75. And we want less than or equal to, so we're shading to the left. And for this, we'll do normal CDF. And then we have negative 10,000. 0.7501, and we end up getting 0.7734. For B, we have z is greater than or equal to negative 1.2. So here's 0, negative 1, negative 2. So negative 1.2 is here. And we want greater than or equal to, so we're shading to the right. This one will be normal CDF. Negative 1.2, 10,000, 1. And for this one, we get 0.8849. For C, we want the probability z is between negative 3 and 0.15. So here's 0, negative 1, negative 2, negative 3. And then we have 1 is here. So negative 3 is right here. 0.15 is going to be here. So C equals negative 3, C equals 0.15, and we're shading between these values. And this one's going to be normal CDF, negative 3, 0.1501, and for this one we'll get 0.5583. For D here, we're looking at the probability that z is between negative 0.87 and negative 0.3. So again, here's 0, here's negative 1. Negative 0.87 is about here. Negative 0.3 is about here. So we're shading in between these. And this one's going to be normal CDF of negative 0.87, negative 0.301, and we're going to get 0.1899. All right, the length of time to complete a door assembly on an automobile factory assembly line is normally distributed with a mean of 6.7 minutes, standard deviation of 2.2 minutes. So again, our mu is 6.7, our sigma is 2.2. For a door selected at random, what's the probability the assembly line time will be 5 minutes or less? So we're looking for the probability that our x is less than or equal to 5 minutes. So normal CDF, negative 10,000 up to 5, mean is 6.7, standard deviation is 2.2, and this will give us 0.2198. For a door selected at random, what's the probability the assembly line time will be 8 minutes or more? So we're looking for the probability that x is greater than or equal to 8. So normal CDF, 8 up to positive 10,000, 6.7, 2.2, and this is going to give us 0.2773. For a door selected at random, what's the probability the assembly line time will be between 6 and 7 minutes? So we're looking at the probability that 6 less than or equal to x less than or equal to 7, because we want between 6 and 7 minutes. So normal, CDF, 6, 7, 6.7, 2.2, and this is going to give us 0.1791. For each of these, you may leave the probabilities as a decimal, or you can write them as a percent. So A would be 21.98%, B would be 27.73%, and C would be 17.91%. Again, decimal to 4 places or percentage is fine. All right, our last section, find the z value described and shade the corresponding area under the standard normal curve for each. A says, find z such that 83.5% of the standard normal curve lies to the left of z. So I want 83.5% to the left. So when we're doing this, I have, here's my 0, here's my 1. If we're unsure where to put this, you can always calculate it first and then draw the curve. It's going to be about here somewhere. And so we can do inverse norm and 0.83501. If you have the calculator that has left, right, center, you also will put in left here. And this will get us 0.97. And so here Z is 0.97. This part is shaded, representing this is our 83.5% to the left of our Z. For B, find Z such that 40% of the standard normal curve lies to the right of Z. So in this case, again, here's our 0, here's our 1. This is 40% is going to be to the right, so we're going to be somewhere about here. Now we want this 40% to the right, which means that we have 60% on the left. So you can do this as inverse norm of 0.601, or if you have the calculator with left, right, center, you can do inverse norm of 0.401 and type right. Either way, this will give us a z value of 0.25. Find z such that 70% of the standard normal curve lies between negative z and z. Well, using our empirical rule, we know that 68% is one standard deviation, so we're going to be just outside the negative 1 and 1 we know here. Label our z's. We know we have a negative z and a positive z. I wrote that negative, but I'll put the negative number once we solve it. So we know this portion here is 70%, meaning there's 30% on the outside, which is split into 15% above and 15% below, or to the left and right. So we can do this as inverse norm 0.1501, or inverse norm, if you have the left, right, center calculator, you can do 0.701 center. Either way, we'll get the same thing. Our z value is going to be positive and negative 1.04. So this is negative 1.04 on the left and positive 1.04 on the right. Okay, suppose the time to take the 6.1 to 6.3 quiz is normally distributed with a mean of 35 minutes and standard deviation 7.5 minutes. So mu is 35, sigma is 7.5. After how many minutes can we expect 70% of the quizzes to be completed? So that means that our first 70% is done. So if we were to draw this on a standard normal curve, we'd be looking at all the way to the left here. This is 70% is completed. And so we're looking for that x value. So we can do inverse norm, and we can do 0.7, and now we can plug in our mean and standard deviation, 35, 7.5. If you have the calculator that has left, right, center, make sure you choose left. And then for this one, we'll get 38.93. So it'd be 38.93 minutes, or about 39 minutes. And our last one, after how many minutes can we expect 25% of the quizzes to be completed? So similar, but now we're looking for our x value here where only 25 have been completed. So we'll do our x is equal to inverse norm of 0.25, 35, 7.5. Again, choose left if you have the calculator that has left, right, center. And this is going to give us 29.94. So 29.94 minutes, or just about 30 or half an hour. And that's our review.